Okay, this is problem 45 and 46 on practice midterm number 3. And the problems is to indicate whether the following homonuclear diatomic compound is A, paramagnetic, or B, diamagnetic. This is another one of those fill in the bubble on the Scantron. So you're going to need to do a lot of the work on scratch paper to understand the underlying reasons. But all you have to do is fill in the bubble at the end of the day. Problem 45 gives boron, B2, the homonuclear diatomic. And so we have to recall the order of the orbitals. Let's construct the molecular orbital set for boron. I start with the atomic orbitals, apparent atomic orbitals for boron, and I'm going to have familiar combinations. A number of orbitals being always conserved. I have 5 orbitals with each atom, so I'm going to have 10 molecular orbitals. So the same number of molecular orbitals are going to be there that were present in the atomic orbitals. And now the key to this problem and a lot of the problems we're going to be dealing with is what comes next from this is the drawing lines correlating the atomic orbitals to the resulting molecular orbitals that arise from them. And so the sigma 2s and the sigma star 2s is pretty straightforward. We know that ordering, and they're going to be split equal distance. The anti-bonding is going to be driven up in energy, the same amount that the corresponding sigma 2s is driven down. The bonding is driven down in energy. But now, what is the energy of the orbitals that arise from combinations of the atomic 2p orbital, atomic orbitals? And it turns out that for boron through nitrogen, the pi, the pi 2p lie lower in energy than the sigma 2p. And now, for all of them, the pi antibonding combination, pi star 2p, is below that of the sigma star 2p. And so for boron B2 through N2, I'm going to have this ordering of the orbitals. So we could just memorize that fact. However, we need to understand why, and then it's not just memorizing a fact. You want to understand the underlying reason, or at least a good explanation for it, the theoretical explanation. Why is this sigma 2p molecular orbital higher in energy than the pi 2p? And the rationale for that is going to be, is best understood when we take into account the nature of the sigma 2s and the sigma 2pz. The 2pz, we're taking the axis, the z-axis, and arbitrarily assigning the axis connecting the atoms as the z-axis. Now, this is what these orbitals look like. I'm going to have one that's going to look at ellipsoidal and one that's an ellipse with 2 little lobes outside. And now, note that both of these are placing electron density in the same region in space. So therefore, there's a lot of repulsive interactions and work that has to be, more work has to be done to place electrons in the same region of space that's already occupied by the lower line sigma 2s. And so that's what drives this energy up above the energy of the pi molecular orbitals. Now, why does this inversion occur when we get to oxygen? And now, to understand that, we need to understand what happens as we proceed across the second row in the periodic table. And in general, what happens as we proceed across the row, we get successively smaller than the size for reasons we've already discussed. And so, because of the increased nuclear charge that's experienced by the valence electrons, as we proceed across the row, we're increasing the number of protons in the nucleus. And that means that as we proceed across, they get smaller, and therefore the electrons are closer to the nucleus and are held more tightly. And this gives rise to the explanation for the increase in electronegativity, fluorine being the most electronegative on the Pauling scale. It holds its electrons very, very tightly, and so, because it's going to be smaller, they can get closer to that nuclear charge. Well, so as we proceed across the second row, from boron, carbon, or nitrogen, and finally to oxygen, what's going to happen is the electron density is not shared as much because it's held more tightly by the successive increase in nuclear charge as I go across the row, and it's more localized on the actual atoms themselves. And so the orbital doesn't have as much electron density, the molecular orbital doesn't have as much electron density in the region between the atoms. It's still a sigma orbital because the electron density lies along the axis connecting the atoms, but it's going to get less and less localized in the region between them, and by the time we get to oxygen, it's mostly localized on the oxygen atom with very little electron density in the region between them. And this is going to be true for the s electrons more than the p electrons, because the s electrons have electron density near the nucleus, whereas the p electrons have a node at the nucleus. So we see as we proceed across this, there's not as much of a change. So I've drawn this cartoon version where you don't see a significant change in the electron density in the sigma 2pz or molecular orbital because of the nature of the atomic orbitals that create it. And so that means that this is placing electron density in a region that doesn't have as much electron density, and so the energy of the sigma 2pz drops down as we proceed across. And eventually, when we get to oxygen, it drops below that of the pi combinations, the pi 2p. And so now we can go back and explain this is the ordering that's going to occur for boron through nitrogen. And that would be, so here's B2. Now I just have to place in the electrons. 1, 2, 3, 1, 2, 3. And I'm going to place the electrons in. There's going to be 6 electrons. I follow Hund's rule. 1, 2, 3, 4, 5, 6. And now, because these are pi electrons, there are 2 of them, are pi orbitals. There are 2 of them of the same energy. So I have to place an electron in, spin up, and another one spin parallel before I start to complete the orbitals. That's Hund's rule, the same rule we used when we were constructing the atomic orbitals. And so this means there exist 2, unpaired. Therefore, is paramagnetic. And that means the answer to 45 is A. That was a lot of work just to fill in a little bubble. But now we go on to 46. I'm not going to have to construct the same, the whole diagram. I can just simply write the orbitals. This is the sigma 2s, the sigma star 2s, the pi 2p, the sigma 2p, pi star 2p, and the sigma star 2p. And now I can just place the electrons in. For carbon, root 4, for C2, I have 4 electrons from each carbon atom. That's going to give me 1, 2, 3, 4, 5, 6, 7, 8. There do not exist unpaired electrons, and therefore it is diamagnetic. That is because of the fact that the pi electrons, or the pi orbitals, are lower in energy than the sigma 2p orbitals. And this is an experimental fact that can be confirmed with a technique known as photoelectron spectroscopy. This ordering of orbitals is experimentally observed. So the answer for 46 is B. And that answers that question.